Mars is a trap disguised as a destination. Step on that red dust and physics starts rewriting your body, bone by bone, cell by cell, until Earth becomes the alien planet and you're the alien who can't survive there anymore. But somehow, this dark reality never makes the headlines. And here is a question for you. If you could choose to instantly understand one mystery of the universe, what would it be? And let me know in the comments. I will pin the most creative answer. Now let's begin. Mars isn't just another destination, it's a test of everything we think we know about survival, endurance, and the limits of human ambition. When we look up at that reddish dot in our night sky, we see promise and possibility. But what astronauts will face there is something entirely different. Let me walk you through why anyone who goes to Mars might never come back, and why this challenge reveals something profound about our place in the cosmos. The journey to Mars takes roughly 6 to 9 months, depending on the alignment of Earth and Mars in their orbits around the Sun. During that time, astronauts face their first major obstacle, cosmic radiation. Unlike Earth, which is shielded by a powerful magnetic field and thick atmosphere, space offers no protection from the relentless barrage of high-energy particles streaming from distant supernova and our own Sun. These particles are called galactic cosmic rays, or GCRs, and they're nothing like the radiation you'd encounter in a medical X-ray. We're talking about particles moving at nearly the speed of light, smashing through spacecraft walls, equipment, and even human tissue. Recent studies published in 2026 by the European Physical Journal analyzed the exact threat these particles pose. Scientists discovered that on a round trip to Mars, an astronaut would absorb radiation doses that approach, or even exceed, NASA's lifetime exposure limits. We're talking about a career's worth of radiation in a single mission. The consequences? Increased cancer risk, cardiovascular damage, and perhaps most disturbing, permanent changes to the central nervous system. Research from 2023 in Space Weather Journal showed that radiation hitting the brain could cause cognitive decline, memory problems, and behavioral changes. Imagine arriving on Mars only to find yourself struggling to remember critical procedures or make clear decisions. But let's say our astronauts make it through the journey and land safely on Mars. That's when the real problems begin. The Martian environment is one of the most hostile places humans have ever seriously considered inhabiting. Think about this. Mars has an atmosphere, but calling it that is generous. The atmospheric pressure on Mars is less than 1% of Earth's. To put that in perspective, it's roughly equivalent to standing 35 kilometers above Earth's surface. At that pressure, without a spacesuit, the fluids in your body would literally begin to boil. Your blood wouldn't immediately boil away like in the movies, but the water in your tissues would vaporize, causing massive swelling. You'd lose consciousness within 15 seconds and be dead in under 2 minutes. And even if you're protected by a suit or habitat, that thin atmosphere creates another problem. It offers almost no protection from radiation. While Earth's astronauts on the International Space Station receive about 50 to 200 millisieverts of radiation per year, Mars explorers would face doses closer to 300 millisieverts annually just on the surface, according to measurements from the Curiosity rover's radiation detector during its journey and early operations. Over the course of a typical Mars mission, lasting anywhere from 500 to 1,000 days, the cumulative exposure becomes a serious health hazard. We're made of stardust, yes, but we're stardust that evolved under the protective blanket of Earth's magnetic field. Stripping that away exposes the fragility of our biology. Here's something else that makes Mars so challenging. Gravity, or rather, the lack of it. Mars has only about 38% of Earth's gravity. You might think that sounds fun, like being able to jump 3 times higher. But your body doesn't see it that way. Your bones and muscles evolved over millions of years in Earth's gravitational pull. Take that away, and your body starts to break down. Astronauts on the International Space Station, which has microgravity, lose 1 to 2% of their bone density per month, despite exercising 2 hours every day. On Mars, with its reduced but still present gravity, the loss might be slower, but it's still significant. Research published in March 2026 in Science Advances revealed something crucial. There's a gravity threshold below which human muscles begin to deteriorate. Scientists exposed mice to different levels of artificial gravity aboard the ISS and found that below 0.67 times Earth's gravity, muscles started breaking down. Mars, with only 0.38 times Earth's gravity, falls well below that threshold. What does this mean? Even with rigorous exercise, astronauts on Mars would experience muscle atrophy. Their hearts, which are also muscles, would weaken. Their bones would become brittle. Over months and years, they'd transform into people whose bodies are adapted to Mars but potentially unable to withstand Earth's gravity ever again. Let's talk about what it would take to bring them home. This is where the engineering challenges become almost insurmountable. Launching from Earth is hard enough. We need massive rockets like the SpaceX Falcon Heavy or the upcoming Starship to escape Earth's gravity well. But at least on Earth, we have infrastructure. We have fuel refineries, manufacturing facilities, and mission control coordinating every detail. Mars has none of that. To return from Mars, astronauts would need a rocket, and that rocket would need fuel. Lots of it. Here's the problem. Bringing all that fuel from Earth isn't practical. The more mass you need to land on Mars, the more fuel you need for the landing. The more fuel you need for landing, the heavier your spacecraft becomes. The heavier your spacecraft, the more fuel you need just to escape Earth's gravity in the first place. It's a vicious cycle that engineers call the tyranny of the rocket equation. Current plans from NASA and SpaceX involve something called in situ resource utilization, or ITSRU. This means using Martian resources to create fuel on Mars itself. The most promising approach involves taking carbon dioxide from Mars' atmosphere, which is 95% CO2, and combining it with water extracted from Martian ice to produce methane and oxygen for rocket fuel. Sounds elegant in theory, but the reality is brutally complex. First, you need to find water ice, extract it, purify it, then build and maintain a chemical plant in one of the harshest environments imaginable. This facility would need to operate flawlessly in temperatures that average -63 degrees Celsius, with daily swings from -75 at night to potentially above freezing during summer days near the equator. The equipment would be exposed to dust storms, radiation, and the corrosive effects of Martian soil, which contains perchlorates, toxic chemicals that are hazardous to both humans and machinery. Even if this fuel production works perfectly, there's another challenge: the sheer amount of fuel needed. SpaceX's Starship design, intended for Mars missions, would require multiple refueling launches in Earth orbit just to have enough propellant to reach Mars. Coming back would require producing over 1,000 metric tons of propellant on Mars. That's not a small operation. That's an industrial facility that needs to function autonomously or with minimal human oversight in an alien environment. Any failure in this system, and the return vehicle becomes a useless hunk of metal. NASA's Mars Sample Return mission, which aims to bring back just small containers of Martian rocks, has faced such enormous technical and financial challenges that the agency had to completely redesign the architecture multiple times. In January 2025, NASA Administrator Bill Nelson announced they were exploring new options after an independent review concluded the original plan could cost up to $11 billion and wouldn't return samples until the 2040 timeframe. If bringing back a few kilograms of rocks is this complicated and expensive, imagine the challenge of bringing back living, breathing human beings who need life support every second of a multi-month journey. Let me paint you an even more concerning picture. The windows for travel between Earth and Mars only open every 26 months when the planets align favorably. Miss your launch window and you're stuck on Mars for over 2 years, waiting for the next opportunity. During that time, you're burning through supplies, your habitat systems are aging, radiation exposure continues accumulating, and your body continues adapting to Martian gravity. The psychological toll of knowing you might be stranded if anything goes wrong is immense. These aren't vacation delays. These are life or death timing constraints governed by the clockwork mechanics of planetary orbits. Now, you might be thinking about the incredible human spirit of exploration and innovation. You're right to think that way. We've overcome enormous challenges before. We've sent 12 humans to walk on the moon and brought them all back safely, minus the Apollo 13 crew's close call. But Mars is fundamentally different from the moon. The moon is 3 days away. Mars is 6 to 9 months away. If something goes catastrophically wrong on the moon, there's at least a theoretical chance of a rescue mission. On Mars, you're utterly, completely on your own. The communication delay alone is between 4 and 24 minutes one way, depending on where Earth and Mars are in their orbits. You can't call home for help and get an immediate answer. Every decision, every emergency has to be handled by the crew with whatever resources they have on hand. Speaking of resources, let's talk about something as basic as breathing. On Earth, you step outside and breathe. Simple. On Mars, the atmosphere is 95% carbon dioxide, 2.6% nitrogen, 1.9% argon, and only 0.13% oxygen. You couldn't breathe Martian air for even a single breath. Every moment outside a habitat requires a spacesuit with its own life support system. Every moment inside requires a habitat that can maintain Earth-like atmospheric pressure and composition. These aren't simple machines. They're complex systems with pumps, filters, sensors, and chemical scrubbers that remove carbon dioxide and regenerate oxygen. The International Space Station uses a system that splits water into hydrogen and oxygen through electrolysis, providing breathable air. The carbon dioxide is removed using chemical scrubbers or venting to space. On Mars, venting to space isn't practical, and the systems must be far more reliable because there's no resupply mission coming every few months, like there is for the ISS. A major failure in the environmental control and life support system on Mars could be catastrophic within hours. NASA engineers have been studying closed-loop life support systems for decades, but creating one reliable enough for a multi-year Mars mission remains one of the critical challenges. If you're finding this fascinating and you want to support this journey of cosmic exploration, please hit that subscribe button and give this video a thumbs up. Your support helps me continue bringing you the wonders and harsh realities of space. And here's something that really shows how different Mars is from anywhere humans have been. Dust. Not just any dust. Martian dust is incredibly fine, almost like talcum powder, and it gets everywhere. The dust particles are also highly oxidized and contain those perchlorates I mentioned earlier. Studies have shown that Martian dust could be harmful if inhaled or if it contaminates food and water supplies. The dust also creates problems for solar panels, machinery, and spacesuits. During the planet-wide dust storm of 2018, which lasted from May through July, NASA's Opportunity rover lost contact and never recovered because its solar panels were completely blocked by dust. The storm created a tau value, a measure of atmospheric opacity that reached 8 to 10 in some areas. For perspective, a clear day on Mars has a tau around 0.5. The entire planet was engulfed in darkness for weeks. If you're interested in learning more about the physics of space travel and what happens at extreme velocities, check out my video called "What Actually Happens If We Reach Light Speed." It explores the mind-bending realities of relativistic travel and connects beautifully to understanding why Mars missions face such fundamental physical constraints. The link is in the description and on the card above. Imagine being an astronaut on Mars during a storm like that. Your solar panels produce almost no power. You're rationing electricity, maybe even oxygen production. You can't see the sun. The psychological impact would be crushing. And these storms can develop with frightening speed. The 2018 storm went from a regional disturbance to planet encircling in just a matter of days. You could be planning an excursion one day and trapped in your habitat the next, with no clear idea when conditions will improve. But let's assume everything goes right. The crew lands safely. The ESRU fuel production works, the habitats function perfectly, everyone stays healthy. Even then, there's the journey home to consider. That return trip carries all the same radiation risks as the outbound journey, but now the astronauts are starting from a compromised physical state. Their bones are weaker, their muscles have atrophied, their cardiovascular systems have adapted to lower gravity. The radiation exposure they've already accumulated means they're even more vulnerable to the additional exposure during the return flight. Studies of astronauts returning from 6-month stays on the ISS show that even with intensive rehabilitation, it takes months to regain bone density and muscle strength. Some astronauts never fully recover. Scott Kelly, who spent 340 days on the ISS from 2015 to 2016, experienced changes to his DNA expression, his microbiome, his cognition, and his physical health that persisted long after returning to Earth. And he was in microgravity, not dealing with the partial gravity of Mars, the radiation environment, or the psychological stress of being on another planet. When these Mars explorers finally make it back to Earth orbit, they face another punishing challenge: re-entry and readaptation to Earth's gravity. After spending potentially 2 to 3 years in reduced gravity environments, their bodies would be profoundly changed. The moment they re-enter Earth's gravitational field at full strength, it would feel like wearing a suit of heavy armor. Their hearts, which had been working in a much easier environment, would suddenly need to pump blood against Earth's full gravitational pull. Standing up could cause dizziness or even fainting as their cardiovascular systems struggle to adjust. Astronaut Chris Hadfield, who spent 5 months on the ISS, described returning to Earth as feeling like he was lying on a bed of broken glass. Every muscle ached, his sense of balance was completely disrupted, and that was after 5 months in microgravity with extensive exercise. Imagine what it would be like after years of Mars gravity. Some researchers have speculated that astronauts returning from multi-year Mars missions might require wheelchairs for weeks or even months. They might experience lasting damage to their bones that increases fracture risk for the rest of their lives. This isn't speculation meant to scare you. This is based on actual data from long-duration spaceflight studies. Here's where the story gets even more profound. We need to talk about what it means to be human in an environment that fundamentally rejects human presence. Earth is the only place in the known universe perfectly suited for human life. We evolved here. Every system in our bodies expects Earth's gravity, Earth's atmosphere, Earth's magnetic protection, even Earth's 24-hour day-night cycle. When you remove those things, you're not just making life uncomfortable, you're challenging the very biological machinery that keeps us alive. There's a concept in biology called the reference environment. It's the environment in which an organism evolved and to which it's optimally adapted. For humans, that's Earth's surface at sea level, with access to liquid water, breathable air, and moderate temperatures. Every step away from that reference environment requires technological intervention to keep us alive. On Mars, we'd be living entirely within artificial ecosystems, completely dependent on technology functioning perfectly, indefinitely. One major system failure, one critical part breaking without a replacement, one unforeseen chemical reaction in the life support systems, and lives could be lost. This brings us to a question that cuts to the heart of the matter. Why go at all? If Mars is this dangerous, if the challenges are this immense, if people might never come back, why are we so determined to go there? The answer reveals something beautiful about the human spirit and our place in the cosmic story. We explore because we're curious. We push boundaries because growth only happens outside comfort zones. We reach for Mars not in spite of the danger, but because overcoming that danger teaches us things we could never learn otherwise. Every challenge Mars presents is also an opportunity for innovation. Figuring out how to produce fuel on another planet advances our chemical engineering and resource utilization knowledge. Developing radiation shielding protects not just Mars astronauts but also patients receiving radiation therapy on Earth. Creating closed-loop life support systems helps us understand Earth's own ecosystems better and could help us develop more sustainable ways of living on our home planet. The technologies we develop for Mars don't stay on Mars, they ripple back to benefit everyone. But beyond the practical benefits, there's something deeper. Mars represents the next chapter in humanity's story. For hundreds of thousands of years, humans lived in Africa. Then we spread across Earth, adapting to deserts, tundras, mountains, and islands. We've always been a species that explores, that asks what's beyond that horizon. Mars is the next horizon. It's the first step toward becoming a multi-planetary species, which might ultimately be necessary for humanity's long-term survival. Physicist Stephen Hawking argued that humanity's long-term survival depends on spreading to other worlds. Earth faces threats both from our own actions and from cosmic events beyond our control. Asteroid impacts, supervolcano eruptions, nearby supernovae, or even our own technological missteps could threaten civilization or even our species. Having a self-sustaining presence on Mars wouldn't guarantee survival, but it would provide redundancy. It would mean that human knowledge, culture, and biology exist in two places instead of one. From a cosmic perspective, that's profound. Now let's talk about the people who would actually make this journey. Who volunteers for a mission knowing they might never return? Throughout history, explorers have embarked on one-way journeys. Polynesian voyagers set out across the Pacific Ocean in outrigger canoes, not knowing if they'd find land or what would await them. Many never returned. European explorers sailed to unknown continents facing disease, starvation, and hostile environments. Arctic and Antarctic explorers ventured into frozen wastelands where rescue was impossible. The Mars volunteers would be part of that same lineage, but with a crucial difference. They'd know exactly what they're getting into. The psychological profile of a Mars astronaut would need to be extraordinary. They'd need technical competence, obviously, but also incredible mental resilience. They'd need to handle isolation, confinement, monotony, danger, and the knowledge that every decision could mean life or death. They'd need to work effectively in small teams for years without outside social interaction. They'd need to cope with the fact that everyone they love is millions of kilometers away and getting farther with each passing day during half of the mission. NASA and other space agencies have conducted isolation studies to understand these psychological factors. The HIC's experiments in Hawaii placed crews in Mars simulation habitats for up to a year. The crews dealt with communication delays, limited resources, and isolation. These studies revealed that even highly trained, motivated individuals experience significant psychological stress. Conflicts arise, depression and anxiety can develop. The monotony of daily routines in confined spaces wears on people, and that's on Earth, where you know you can leave if there's an emergency. On Mars, there's no leaving. Some researchers have proposed that the first Mars missions should be one-way by design. The Mars One project, proposed in the early 2010s, envisioned sending volunteers to establish a permanent Mars colony with no return capability. The idea was controversial and ultimately failed due to financial and technical problems, but it raised important questions. If we're honest about the difficulties of returning from Mars, should we stop pretending it's a round trip? Should we instead focus on making Mars habitable for those who go? This idea divides the space community. Some argue that one-way missions are unethical, that we shouldn't ask people to sacrifice their return to Earth. Others counter that if individuals understand the risks and volunteer anyway, it's no different from other dangerous professions or historical explorations where return was uncertain. The ethical debates are complex, touching on questions of informed consent, the value we place on human life, and what we owe to those who venture into the unknown on behalf of all humanity. But here's something fascinating. When surveys have asked people if they'd volunteer for a one-way Mars mission, a surprising number say yes. A poll conducted by Mars One back in 2013 received over 200,000 applications from people willing to leave Earth forever. These weren't uninformed dreamers. Many were scientists, engineers, and skilled professionals who understood the risks. They saw it as the ultimate adventure, the chance to be part of something bigger than themselves. They wanted to be pioneers of a new world. What drives that kind of commitment? Part of it is the allure of exploration, that fundamental human desire to see what lies beyond. Part of it is the chance for immortality, not in the biological sense, but in the historical sense. The first humans on Mars will be remembered as long as human civilization exists. Their names will be spoken with the same reverence we give to Magellan, Amundsen, Armstrong, and Aldrin. Part of it is also a recognition that life on Earth, for all its comforts, can feel limiting to certain personalities. Mars offers a blank slate, a chance to build something new. Let me share something that puts all this into perspective. We are made of stardust. This isn't poetic metaphor, it's literal truth. The carbon in your muscles, the calcium in your bones, the iron in your blood, all of it was forged in the nuclear furnaces of stars that exploded billions of years ago. Those elements scattered across space, eventually condensing into the solar system, the Earth, and ultimately, you. We're the universe becoming conscious of itself, able to look back and wonder about our origins. Mars is made of the same stardust, formed in the same stellar nursery as Earth 4.6 billion years ago. When we stand on Mars, we're not visiting a completely alien world. We're returning to a sibling planet, another child of the Sun, exploring our cosmic family. The red dust beneath an astronaut's boots contains iron oxide, the same substance that makes blood red and rust orange. The water ice hidden beneath the surface follows the same chemical laws as Earth's oceans. The rocks tell stories of ancient rivers and lakes that dried up billions of years ago, hinting at a time when Mars might have been more Earth-like. This connection makes the challenges even more poignant. If Mars was once more hospitable, what happened? Why did it lose its magnetic field? Why did its atmosphere escape to space? Why did its water disappear? Understanding Mars' past helps us understand planetary evolution in general, including Earth's future. Our magnetic field won't last forever. Our atmosphere could theoretically be stripped away over geological time. Mars is a cautionary tale and a laboratory all at once. The loss of Mars' magnetic field, which happened around 4 billion years ago, was catastrophic for the planet. Without that protective shield, the solar wind, a stream of charged particles flowing from the Sun, began stripping away the atmosphere. Over millions of years, Mars transformed from a world with rivers, lakes, and possibly even oceans to the frozen desert we see today. The NASA MAVEN mission, which has been orbiting Mars since 2014, has measured this atmospheric loss happening in real time. Mars is still losing atmosphere to space at a rate of about 100 grams per second. That might not sound like much, but over billions of years, it's transformed the entire planet. This history matters for future Mars explorers because it means the planet is actively hostile to atmospheres. If we tried to terraform Mars to make it more Earth-like by thickening the atmosphere and warming the surface, the same solar wind would constantly work against us, stripping away whatever atmosphere we created. Without restoring Mars' magnetic field, a challenge so enormous it's barely within the realm of theoretical possibility, any atmosphere we build would be temporary on cosmic timescales. Some visionary scientists have proposed wild ideas to address this. One concept involves placing a massive magnetic shield at the L1 Lagrange point between Mars and the Sun, creating an artificial magnetosphere that would protect the planet. NASA's Planetary Science Division actually presented this idea at a workshop in 2017. The shield would need to generate a magnetic field strength of 1 or 2 Tesla, similar to an MRI machine, but stretched across thousands of kilometers. With current technology, this is pure science fiction, but it shows how seriously scientists think about making Mars more habitable for the long term. Even without terraforming the entire planet, we might create localized habitable zones. Imagine vast domed cities or underground habitats where atmospheric pressure and composition are controlled. These wouldn't be temporary research stations like Antarctic bases. They'd be permanent settlements where children are born and grow up, where Martian culture develops, where humanity becomes a two-planet species. Those children, born and raised in Martian gravity, would face their own unique challenge. They might never be able to visit Earth. Think about that for a moment. A child born on Mars, growing up in 38% of Earth's gravity, would develop a body adapted to that environment. Their bones would be less dense, their muscles configured for lower gravitational loads, their cardiovascular system calibrated to pump blood in easier conditions. If they came to Earth as a teenager or adult, Earth's gravity might be dangerously overwhelming. They might not have the bone strength to support their own weight. Their heart might not be able to pump effectively against the increased gravitational pressure. In a very real sense, Mars-born humans might be trapped there by their own biology. This creates a profound question about human identity and belonging. Would Mars-born humans consider themselves human in the same way we do? Would they develop their own culture, distinct from Earth's? Would there eventually be tension between Earth and Mars, the way colonial populations on Earth sometimes clashed with their home nations? These aren't just science fiction scenarios, they're logical consequences of establishing a permanent human presence on another world. Let's zoom out for a moment and consider the bigger picture. In the 13.8 billion year history of the universe, in the 4.5 billion year history of Earth, in the 300,000 year history of Homo sapiens, we're living in an extraordinary moment. We're the first generation with the technical capability to reach other planets. We're standing at a threshold that will define humanity's future for thousands or millions of years to come. The decisions we make now about Mars exploration will echo through time. The cosmos doesn't care about our plans or our dreams. It operates on physical laws that are indifferent to human ambition. Gravity doesn't negotiate. Radiation doesn't make exceptions. The vacuum of space doesn't offer second chances. This isn't meant to discourage us, it's meant to ground our excitement in reality. The universe is not hostile to life, but it's not hospitable either. It simply is. And within that indifferent cosmos, we're trying to carve out new spaces for human existence. This brings us to one of the most sobering aspects of Mars exploration: the medical challenges. We've touched on radiation, bone loss, and muscle atrophy, but there are other concerns that keep space medicine specialists awake at night. One is vision impairment. Astronauts on long-duration missions to the ISS have experienced a condition called spaceflight-associated neuroocular syndrome, or SANS. The fluid shifts that occur in microgravity cause pressure on the optic nerve and changes to the eyeball's shape. Some astronauts have returned with permanent vision changes. On Mars, with its partial gravity, would this problem be better, worse, or the same? We honestly don't know. There's no data on how human physiology responds to long-term exposure to Martian gravity because no human has ever experienced it. We're extrapolating from microgravity studies and making educated guesses. This uncertainty itself is a risk. We might discover problems we never anticipated only after astronauts are already on Mars, too far away to come home quickly if medical intervention is needed. Consider something as routine as surgery. On Earth, we take for granted that if something goes wrong medically, we can get to a hospital with specialists, imaging equipment, and a full pharmacy. On Mars, the crew's medical officer would need to handle everything from routine injuries to potentially life-threatening emergencies with only the supplies they brought and whatever they can improvise. What if someone develops appendicitis? What if there's a traumatic injury during a surface excursion? What if someone has a heart attack or stroke? Surgeons have practiced procedures in microgravity, but it's incredibly difficult. Bodily fluids float around, instruments drift away. Keeping a sterile field is challenging. On Mars, the gravity would help with some of these issues, but the sterility concerns remain. Mars dust contains perchlorets and other potentially toxic compounds. Keeping that dust out of a surgical area would be critical but difficult, and there's no calling for backup. No medevac helicopter is coming. The medical team works with what they have, or the patient dies. Then there's the question of reproduction. If humans establish a permanent presence on Mars, eventually people will want to have children. But can human reproduction even work normally in Martian gravity? Studies of mammalian reproduction in microgravity have shown problems with fertilization, embryonic development, and pregnancy. Mouse embryos grown in space have shown developmental abnormalities. We have no data on whether partial gravity like Mars provides is sufficient for normal human pregnancy and fetal development. There's also the radiation concern during pregnancy. A developing fetus is particularly vulnerable to radiation damage because the cells are dividing so rapidly. On Earth, we shield pregnant women from X-rays and other radiation sources as much as possible. On Mars, that constant background radiation can't be avoided without substantial shielding. Would Mars-born children have higher rates of birth defects or developmental problems? We can hypothesize and model, but we won't really know until it happens. Those first Mars-born children would be pioneers in the most profound sense, testing whether humanity can truly reproduce beyond Earth. Let's shift gears and talk about the infrastructure needed to make Mars even remotely survivable. We're not just talking about a spaceship and some supplies, we're talking about building an entire civilization's worth of capability on a world that starts with nothing. Every calorie of food, every liter of water, every breath of air, every watt of power, all of it must be produced, recycled, or imported from Earth at enormous cost. Food production is one of the biggest challenges. Early missions would bring freeze-dried and preserved food from Earth, but that's not sustainable long-term. To become self-sufficient, Mars colonists would need to grow their own food. This means greenhouses, but not like any greenhouse on Earth. Martian greenhouses would need to be pressurized, heated, shielded from radiation, and provided with artificial light or clever systems to concentrate the weak Martian sunlight. The soil itself is another problem. Martian regolith, the loose, dusty material covering the surface, isn't really soil in the Earth sense. It lacks the organic matter and beneficial microorganisms that make Earth soil fertile. It contains those toxic perchlorets I mentioned earlier, which would need to be washed out or neutralized before plants could safely grow in it. Astronauts would essentially need to create soil from scratch, perhaps combining Martian regolith with composted organic waste and carefully managed microbial cultures. Growing plants on Mars also means dealing with the day-night cycle. A Martian day, called a sol, is about 24 hours and 40 minutes long, conveniently close to Earth's day. But the light levels are much lower than on Earth because Mars is farther from the Sun. Earth receives about 1,370 watts of solar energy per square meter at the top of the atmosphere. Mars receives only about 590 watts per square meter. That's less than half. Plants evolved for Earth light levels might struggle or grow more slowly under Martian conditions, even inside a greenhouse. NASA has conducted extensive studies on this, including the veggie experiments on the ISS, where astronauts successfully grew lettuce, zinnia flowers, and other plants in microgravity. These experiments show it's possible, but the ISS has the advantage of being resupplied regularly and having mission control constantly monitoring systems. Mars colonies would need robust, reliable systems that can operate with minimal intervention and repair themselves when possible. Water is another critical resource. We know Mars has water ice both at the poles and buried beneath the surface at various locations. The Phoenix lander in 2008 confirmed water ice just below the surface in the northern polar region. The Mars Reconnaissance Orbiter has detected vast ice deposits in mid-latitudes. The question isn't whether Mars has water, but whether we can access it efficiently and purify it for human use. Extracting water ice from beneath the Martian surface means digging or drilling then melting the ice and purifying the resulting water. This requires energy, lots of it. Then the water must be split into hydrogen and oxygen for breathable air and rocket fuel, stored for drinking and agriculture, and recycled through life support systems. Water recycling on the ISS recovers about 93% of water from urine and humidity condensation. On Mars, we'd need to push that efficiency even higher because importing water from Earth is prohibitively expensive. Power generation on Mars presents its own unique set of obstacles. Solar panels work, but they're less efficient than on Earth due to the reduced sunlight and the constant problem of dust accumulation. The 2018 global dust storm that killed the Opportunity rover showed how devastating dust can be. Imagine relying on solar power for life support when a dust storm blocks 90% of sunlight for weeks or months. You'd need battery storage capacity that could sustain an entire habitat through extended periods of darkness, which means massive, heavy batteries that are expensive to transport from Earth. Nuclear power is the obvious alternative. A small nuclear reactor could provide continuous power regardless of dust storms, day-night cycles, or seasonal variations. NASA has developed the Kilopower reactor, a compact fission system designed for space applications. In tests conducted in 2018, the prototype successfully demonstrated that it could produce up to 10 kilowatts of electrical power continuously for years. For a Mars base, you'd probably want multiple reactors for redundancy, providing enough power for life support, food production, water processing, scientific research, and eventually industrial production. But nuclear reactors bring their own challenges. They need cooling systems, which on Mars would require careful engineering since there's no flowing water for traditional cooling. They produce radioactive waste that must be stored safely. They require maintenance by people trained in nuclear engineering. And there's always the psychological factor, living next to a nuclear reactor on an alien planet, knowing that if something goes wrong, there's no evacuation route. It's perfectly safe when designed and operated correctly, but the human mind doesn't always respond rationally to nuclear technology. Manufacturing and repair capabilities are absolutely essential for long-term survival. You can't bring every possible spare part from Earth. A permanent Mars presence would need workshops with 3D printers, metal fabrication equipment, electronics repair tools, and raw materials. The colonists would need to become expert at improvisation and repair, much like astronauts on the ISS, but with far less ability to call home for advice or wait for replacement parts. There's promising research in this area. Scientists have experimented with using Martian regolith as a feedstock for 3D printing, essentially making bricks and structural components from local materials. The European Space Agency has tested 3D printing techniques using simulated Martian soil. In 2019, researchers at Northwestern University developed a method to 3D print structures using synthetic Martian and lunar dust mixed with simple biopolymers. These technologies could allow colonists to build habitats and structures without importing massive amounts of construction material from Earth. But there's a limit to what can be manufactured locally, at least initially. Complex electronics, medical equipment, specialized tools, these would still need to come from Earth for the foreseeable future. This creates a vulnerable dependency. A permanent Mars colony would never be truly independent as long as it relies on Earth for critical supplies. Breaking that dependency would require building up an industrial base on Mars that can manufacture increasingly complex items, a process that would take decades at minimum. Communication with Earth introduces another layer of complexity to daily life on Mars. That 4 to 24-minute one-way light delay means real-time conversation is impossible. Imagine calling home and having to wait 8 to 48 minutes for a response to any question. You can't have a natural conversation. You can't get immediate emotional support. Everything becomes asynchronous, like exchanging emails, but even slower. For the colonists, this would create a profound sense of isolation. Earth would be visible in the night sky, a bright blue star, but completely unreachable. They'd watch news from home that's already 10 to 50 minutes old by the time they see it. They'd send messages to loved ones knowing the reply won't arrive for at least 8 minutes. And during opposition, when Earth and Mars are on opposite sides of the Sun, communication could be disrupted entirely for weeks. This isolation would force Mars colonists to become psychologically independent. They couldn't rely on Earth for quick decisions or guidance. Colony leadership would need to make critical choices without waiting for approval from mission control. Over time, this autonomy would likely breed a distinct Martian culture and identity. The colonists would share experiences and challenges that no one on Earth could truly understand. They'd develop their own traditions, their own way of speaking, perhaps eventually their own values and priorities. History shows us that geographic isolation breeds cultural divergence. The Polynesian cultures spread across the Pacific developed distinct languages, traditions, and social structures despite common origins. European colonies in the Americas eventually developed identities separate from their parent nations. It's not hard to imagine that within a few generations, Mars colonists would think of themselves as Martians first and Earthlings second, if at all. This raises political questions that might seem premature but are actually important to consider now. Who governs Mars? If a colony is established by NASA, does the United States claim sovereignty? If it's a SpaceX venture, does a private company own a planet? The Outer Space Treaty of 1967, signed by over 110 countries, states that celestial bodies cannot be claimed by nations and should be used for peaceful purposes for the benefit of all humanity. But the treaty was written in an era when permanent space settlement seemed like distant science fiction. As Mars colonies become real, these legal frameworks will be tested. If someone commits a crime on Mars, which legal system has jurisdiction? If Mars colonists want political independence, do they have that right? If resources are discovered on Mars, rare metals for instance, who owns them? These aren't abstract questions. They'll have real answers with real consequences for how humanity expands beyond Earth. Let me share something that might surprise you. Despite all these challenges, all the dangers, all the reasons why going to Mars is monumentally difficult and why people might never return, I believe we should still go, not recklessly, not without proper preparation, but purposefully and deliberately. Here's why: because the alternative is stagnation. Humanity faces existential risks on Earth. Climate change, nuclear weapons, pandemics, asteroid impacts, artificial intelligence gone wrong. The list goes on. Having all of humanity concentrated on one planet means a single catastrophe could end our story. Spreading to Mars doesn't eliminate these risks, but it provides redundancy. It means that human knowledge, culture, and biology exist in two separate locations, making total extinction slightly less likely. Beyond survival, there's the question of meaning and purpose. Humans need challenges. We need frontiers. Throughout history, societies that stopped exploring and innovating eventually stagnated or declined. The process of reaching for difficult goals drives innovation, inspires young people to pursue science and engineering, and reminds us that we're capable of extraordinary things when we work together toward a common vision. The Apollo program is a perfect example. The goal of landing humans on the moon by the end of the 1960s seemed impossible when President Kennedy announced it in 1961. The technology didn't exist. Many of the scientific principles hadn't been worked out. Yet within 8 years, Neil Armstrong and Buzz Aldrin walked on the lunar surface. The innovations developed for Apollo didn't stay in space. They revolutionized computing, telecommunications, materials science, and countless other fields. The inspiration from Apollo launched millions of young people into STEM careers. Mars can do the same thing, but even more so because Mars is a much harder challenge than the Moon. The Moon is 3 days away, Mars is 6 to 9 months away. The Moon has no atmosphere to complicate landing, but also no resources to use. Mars has both challenges and opportunities. Solving the Mars problem requires innovations in propulsion, life support, medicine, psychology, energy production, food systems, manufacturing, robotics, artificial intelligence, and more. These innovations will benefit everyone, not just the astronauts who go to Mars. Consider closed-loop life support systems as an example. To keep humans alive on Mars, we need to recycle everything: air, water, waste, with near-perfect efficiency. Developing these systems teaches us how to create sustainable, self-contained ecosystems. This knowledge applies directly to sustainability challenges on Earth. How do we design cities that recycle all waste and minimize environmental impact? How do we create sustainable agriculture that doesn't deplete soil or require constant chemical inputs? The engineering principles are similar. Or think about the medical innovations required for Mars missions. Telemedicine and remote surgery techniques developed for astronauts millions of kilometers from Earth could help people in remote areas on Earth access better health care. Compact diagnostic equipment that fits in a Mars habitat could be deployed to field hospitals or developing regions. Techniques for maintaining physical and mental health during long isolation could help submariners, Antarctic researchers, or even people in isolation due to pandemics. The point is this: reaching for Mars makes us better at solving problems on Earth. It forces us to think systematically about resource management, sustainability, resilience, and long-term planning. These are exactly the skills we need to address Earth's challenges. The space program isn't a distraction from Earth's problems, it's a catalyst for solving them. Now, I want to address a common criticism of Mars exploration: the cost. People rightly ask, why spend billions of dollars on Mars when we have poverty, hunger, disease, and environmental destruction right here on Earth? It's a fair question and deserves a thoughtful answer. First, space exploration is a tiny fraction of government budgets. NASA's budget is currently about $25 billion per year, which sounds enormous until you realize the US federal budget is around $6 trillion. NASA gets less than half of 1%. For perspective, Americans spend more on pizza delivery each year than the entire NASA budget. Second, the money doesn't go to Mars, it stays on Earth. It pays salaries to scientists, engineers, technicians, and support staff. It funds research at universities. It goes to companies building hardware and software. The economic activity generated by space exploration creates jobs and drives technological advancement. Studies have shown that for every dollar invested in NASA, the American economy receives approximately $7 to $14 in return through technological innovation, job creation, and economic activity. Third, and perhaps most importantly, we don't have to choose between Earth and space. We can do both. In fact, we must do both. The same societies that invest in space exploration also tend to invest in education, healthcare, infrastructure, and scientific research. The skills, knowledge, and inspiration generated by space programs make us better equipped to solve terrestrial problems. Countries with active space programs tend to be leaders in science, technology, and innovation across all sectors. But let's be brutally honest about something. The first Mars missions will almost certainly be expensive, dangerous, and possibly end in tragedy. Space exploration has always involved risk. The Apollo 1 fire killed 3 astronauts during a ground test in 1967. The Challenger shuttle exploded 73 seconds after launch in 1986, killing 7 crew members. The Columbia shuttle disintegrated during re-entry in 2003, killing another 7. Each tragedy was devastating, but humanity continued exploring because the people who died believed the mission was worth the risk, and because we learned from each failure and made the next attempt safer. Mars will likely claim lives too. A landing might fail. A habitat might depressurize. A dust storm might overwhelm power systems. Someone might develop a medical condition that can't be treated with available resources. These possibilities aren't reasons to stay home, they're challenges to prepare for and minimize. Every explorer in history faced mortal danger. Many didn't return, but their sacrifices advanced human knowledge and capability, and the volunteers for Mars will go with eyes open, knowing the risks, believing the goal is worth it. There's a quote often attributed to various explorers and adventurers. "A ship in harbor is safe, but that's not what ships are built for." Humanity in Earth's gravitational well is safe, relatively speaking, but that's not what humanity is built for. We're built to explore, to push boundaries, to ask what if and what's next. Mars calls to that fundamental aspect of human nature. Let me tell you about some of the people already working to make Mars a reality. Elon Musk, whatever you think of him personally, has dedicated much of his fortune and his life to making humanity multiplanetary. SpaceX, the company he founded, has revolutionized spaceflight with reusable rockets, dramatically lowering the cost of getting to orbit. The Starship system currently in development is designed specifically for Mars missions, with the capability to carry 100 people and over 100 tons of cargo to the Martian surface. When Musk talks about Mars, he speaks with an urgency born from the belief that humanity is in a race against time. Civilizations can decline. Technology can be lost. He points to historical examples like the Library of Alexandria burning or the Roman Empire's fall leading to the Dark Ages. His argument is that we have a window of opportunity while we have the technological capability and economic resources to reach Mars, and we should use that window while we can. Whether you agree with his timeline or methods, the underlying concern is valid. There's no guarantee that Earth civilization will always be stable and prosperous enough to fund interplanetary expansion. NASA, meanwhile, pursues a more measured approach. The Artemis program aims to return humans to the Moon first, establishing a sustainable presence there and using it as a proving ground for Mars technologies. The idea is sensible. The Moon is close enough that if something goes wrong, help can arrive in days rather than months. It's a testbed for habitats, spacesuits, rovers, resource extraction, and long-duration operations in a hostile environment. The lessons learned on the Moon transfer directly to Mars, but with a safety net that Mars won't provide. China has also announced ambitious Mars plans. Their space program has advanced rapidly over the past 2 decades. They've successfully landed rovers on the Moon, including on the far side where no one else has operated. In 2021, China's Tianwen-1 mission successfully placed a rover named Zhurong on Mars, making China only the second nation to successfully operate a rover on the Martian surface. Chinese officials have discussed crewed Mars missions potentially in the 2030s or 40s. If history is any guide, international competition in space can accelerate progress, just as the space race between the US and Soviet Union drove rapid advancement in the 1960s. The European Space Agency, Russia's Roscosmos, India's ISRO, and even private ventures from various countries are all developing Mars-related capabilities. This international interest is encouraging because Mars is big enough for everyone. There's no need for territorial conflicts or exclusive claims. Multiple nations and organizations could establish separate bases, share scientific data, and create a diverse Martian presence that's more resilient than any single national effort could be. Collaboration makes sense for another reason. No single nation or company possesses all the expertise and resources needed for successful Mars colonization. The United States leads in some areas, Europe in others, China in still others. Pooling knowledge and resources like the international cooperation that built and maintains the ISS could make Mars missions safer, cheaper, and more successful. The political will for such cooperation is uncertain, especially given current global tensions, but the practical benefits are undeniable. Let's talk about what early Mars bases might actually look like. Forget the science fiction images of gleaming domed cities. The first habitats will likely be partially buried or covered with regolith for radiation protection, connected by tunnels rather than exposed walkways. They'll be cramped, utilitarian, and constantly requiring maintenance. Think less Star Trek and more Antarctic research station, but with the volume turned up on every difficulty. The base would probably start with pre-positioned cargo missions. Before humans even launch from Earth, multiple cargo spacecraft would land on Mars, carrying habitats, life support equipment, solar panels or nuclear reactors, water extraction equipment, food supplies, rovers, scientific instruments, and return vehicles. Robots and autonomous systems would begin setup, but much would wait for human arrival. This pre-positioning reduces risk. If a cargo mission fails, you send a replacement before committing human lives. When the crew finally lands, their first priority would be establishing reliable life support and shelter. Every system would need to be checked, double-checked, and tested. Remember, there's no calling a repair person. If the oxygen generator fails and can't be fixed, everyone dies. The psychological pressure of living with that reality every single day would be immense. These astronauts would need not just technical competence, but exceptional emotional resilience and the ability to stay calm and methodical under extreme stress. Daily life on Mars would revolve around routine maintenance, scientific research, and survival tasks. A typical schedule might include checking and maintaining life support systems, tending to plants in the greenhouse, conducting geological surveys and experiments, exercising to maintain muscle and bone health, preparing and eating meals, communicating with Earth within the constraints of the time delay, and managing the psychological challenges of isolation and confinement. Social dynamics in such close quarters would be critical. On the ISS, crews typically rotate every 6 months. If interpersonal conflicts develop, people know they'll be going home soon. On Mars, the crew is stuck together for years. Psychological screening and team compatibility become absolutely crucial. NASA already pays enormous attention to crew selection, looking not just for technical skills but for emotional stability, conflict resolution abilities, sense of humor, and the capacity to thrive rather than merely survive in extreme environments. Interestingly, studies have shown that mixed-gender crews often have better social dynamics than single-gender crews on long-duration missions. The presence of both men and women tends to moderate behavior and create more balanced social environments. This has implications for crew selection. Mars missions will almost certainly be mixed gender, which raises questions about relationships, privacy, and yes, eventually, sex and reproduction in space. These are topics that make mission planners uncomfortable, but they're realities that must be addressed for long-duration missions. Privacy itself becomes a precious commodity. On the ISS, astronauts have tiny sleeping quarters about the size of a phone booth. On Mars, habitat space would be at a premium. Private space for each crew member would be minimal. Imagine living in a small apartment with 5 other people for 2.5 years, never able to step outside without a spacesuit, never able to take a walk alone in nature, never able to escape the hum of life support machinery. It's a level of confinement that most people have never experienced and couldn't tolerate. There have been analog missions on Earth that simulate these conditions. The HIC's program in Hawaii housed crews in a Mars-like habitat on the slopes of Mauna Loa for missions lasting up to a year. Crews wore spacesuits when venturing outside, ate preserved food, dealt with communication delays, and lived in isolation. These missions revealed that even highly motivated, carefully selected people struggle with the psychological challenges. Conflicts arise, motivation wanes. People develop strategies to cope, establishing personal routines, creating privacy within shared spaces, and finding ways to maintain individual identity within the collective. One HIC's crew member described the experience as simultaneously the most difficult and most meaningful thing they'd ever done. The hardship created bonds between crew members that resembled military units in combat, people who've shared extreme experiences that outsiders can't fully understand. This suggests that Mars crews would develop incredibly strong bonds, but also that reintegration with normal Earth society might be difficult if they ever return. The question of returning from Mars is itself complicated. Early missions would almost certainly be round-trip, with astronauts staying on Mars for 18 to 20 months, waiting for the planets to align favorably for the return journey, then spending another 6 to 9 months in transit back to Earth. That's roughly 2.5 to 3 years total mission time, with most of it spent on or traveling to Mars. After that long in reduced gravity environments, the astronauts' bodies would be significantly deconditioned. Returning to Earth's full gravity would be brutal. Astronauts returning from 6-month ISS missions can barely walk when they first land. They need to be carried from the spacecraft. Their muscles are weakened, their bones are less dense, their cardiovascular systems struggle to pump blood against Earth's gravity. It takes months of rehabilitation to recover, and some changes like bone density loss may never fully reverse. Now imagine that effect amplified by a mission 3 to 5 times longer, with months spent in Martian partial gravity that allows further deconditioning. Some scientists have speculated that after a certain threshold, perhaps a few years on Mars, return to Earth might become medically inadvisable or even impossible. The human body might adapt so thoroughly to Martian conditions that Earth's gravity would be intolerable. This raises a disturbing possibility. Some Mars astronauts might be making a one-way trip without fully realizing it. They might technically have a return spacecraft available, but using it could kill them or leave them permanently disabled. This brings us to the concept of one-way missions, which has been seriously proposed. The Mars One project, announced in 2012, planned to send colonists on a one-way trip to establish a permanent settlement. Volunteers would accept from the beginning that they'd never return to Earth, living out their lives on Mars. The project attracted thousands of applicants despite the obvious risks and was widely covered in media. Ultimately, Mars One went bankrupt in 2019 without launching anything, but the concept revealed something important. There are people willing to accept a one-way trip to Mars. Why would anyone volunteer for such a mission? For some, it's the ultimate adventure, being among the first humans to live on another planet, writing your name permanently into history. For others, it's about contributing to something larger than themselves, sacrificing personal comfort for humanity's future. Some see it as escape from Earth's problems or constraints. And yes, some probably haven't fully thought through what they're volunteering for, romanticizing the idea without understanding the reality. From a practical standpoint, one-way missions have certain advantages. Eliminating the return vehicle reduces mission mass significantly, allowing more supplies and equipment to be sent. The crew could focus entirely on establishing a sustainable base rather than maintaining a return capability. Psychologically, accepting from the outset that you're staying might be easier than spending years on Mars constantly preparing for and anticipating a difficult return journey. But there are profound ethical questions. Is it acceptable to send people on missions they can't return from? What if conditions turn out to be worse than expected? What if someone changes their mind after arriving? The counter-argument is that adults should be free to accept risks they understand, just as people choose dangerous professions like deep-sea fishing, mining, or military service. As long as the volunteers are fully informed and mentally competent, perhaps it's paternalistic to deny them the choice. Personally, I believe early missions should maintain return capability, even if some crew members choose not to use it. Having the option provides psychological security and allows for medical evacuation if something goes catastrophically wrong. Once a base is well established with proven life support and food production, then perhaps permanent colonization makes sense. But sending people one way on the very first missions, when so much is unknown, feels unnecessarily risky. Let's consider what success on Mars actually looks like in the long term. True success isn't just landing humans on Mars or even keeping them alive there for a few years. Success means establishing a self-sustaining presence that can survive and grow without constant support from Earth. This requires achieving several milestones that will take decades at minimum. First, the colony must become food independent. The greenhouses must produce enough calories to feed the population without imports from Earth. This means mastering Martian agriculture, developing crop varieties suited to local conditions, and creating closed-loop systems where waste becomes fertilizer and nothing is wasted. It's a massive challenge because Earth's agricultural systems evolved over 10,000 years. Mars colonists need to compress that learning into decades. Second, the colony must achieve water and air independence. Water must be extracted from Martian ice and recycled with near-perfect efficiency. Oxygen must be produced from water electrolysis or extracted from the carbon dioxide atmosphere using technologies like MOXIE, Mars, Oxygen in situ resource utilization experiment, which successfully produced oxygen on Mars with NASA's Perseverance rover in 2021. These systems must be reliable enough that the colony could survive indefinitely even if no more shipments arrived from Earth. Third, the colony needs manufacturing capability. Initially, this might be limited to basic items, simple tools, spare parts, construction materials made from regolith. Over time, it must expand to more complex manufacturing, electronics, medical equipment, vehicle components, eventually perhaps even spacecraft. This requires developing an entire industrial base, from raw material extraction through processing, manufacturing, and quality control. Earth took centuries to build this capability. Mars needs to do it faster. Fourth, and perhaps most challenging, the colony needs energy independence. Solar panels and nuclear reactors are fine for early bases, but a growing colony needs growing power generation. Expanding solar arrays requires manufacturing capability. Building additional nuclear reactors requires importing highly specialized components from Earth or developing the capability to produce them locally. Eventually, perhaps Mars could utilize fusion power if that technology matures, but that's speculative at this point. Fifth, the colony needs intellectual and cultural independence. This doesn't mean severing ties with Earth, but it means developing unique knowledge, skills, and culture that aren't just imported Earth culture. Mars colonists would become experts in Martian geology, climate, and ecology in ways that Earthbound scientists never could be. They'd develop engineering solutions specific to Martian conditions. They'd create art and literature reflecting their unique experiences. They'd form their own identity. When all these pieces come together, food, water, air, manufacturing, energy, and culture, then you have a truly self-sustaining Mars civilization. The timeline for achieving this is highly uncertain. Optimistic estimates suggest 50 to 100 years after the first human landing. More conservative estimates range from 100 to 200 years or more. The truth is, nobody knows because we've never done anything remotely like it before. Population growth on Mars presents its own fascinating challenges. For a colony to be truly sustainable, needs a population large enough to maintain genetic diversity, preserve knowledge across generations, and provide all the specialized skills necessary for survival. Studies suggest a minimum viable population for long-term survival might be anywhere from 500 to several thousand people. Below that threshold, genetic bottlenecks and random accidents could threaten the colony's survival. But how does that population grow? Natural reproduction in Martian gravity is completely unstudied in humans. We have no idea if human conception, pregnancy, and fetal development would proceed normally in 0.38 Earth gravity. Animal studies in space have shown complications, but these were conducted in microgravity, not partial gravity. It's possible that Mars gravity is sufficient for normal development, or it might cause serious problems. We simply don't know, and we won't know until someone becomes pregnant on Mars, which raises enormous ethical questions about who bears that risk. If natural reproduction proves difficult or impossible on Mars, the colony would depend entirely on immigration from Earth. This creates a permanent dependency and makes Mars more of an outpost than a true second home for humanity. Alternatively, technology might provide solutions, artificial wombs, genetic modifications to adapt humans to Martian conditions, or rotating habitats that provide Earth normal gravity for pregnant women. But these solutions range from speculative to science fiction. Assuming reproduction is possible, children born on Mars would be the first true Martians. They'd never know Earth except through videos and stories. Their bodies would develop in Martian gravity, possibly making them taller and differently proportioned than Earth humans. They'd grow up wearing space suits, living in enclosed habitats, seeing Earth as a bright blue star in the night sky. Their psychology, culture, and identity would be fundamentally different from any humans who've ever lived. These Martian-born children might also face a tragic limitation. They might never be able to visit Earth. Bodies that develop in Martian gravity might not be able to adapt to Earth's higher gravity. A person born on Mars might find Earth's gravity crushing, making breathing difficult, putting dangerous stress on their heart and bones. They'd be permanent exiles from humanity's homeworld, able to communicate with Earth but never visit it. This reality could create a permanent division between Earth humans and Mars humans, two branches of humanity adapted to different worlds. Terraforming Mars, transforming it into an Earth-like world with a breathable atmosphere, liquid water, and moderate temperatures, is often proposed as the ultimate solution. The idea is conceptually simple: release greenhouse gases to warm the planet, melt the ice caps, and create a thicker atmosphere. Import nitrogen and oxygen or produce them from Martian materials. Introduce engineered microorganisms that can survive Martian conditions and gradually make the environment more Earth-like. Over centuries or millennia, transform Mars into a second Earth. The reality is enormously more complicated. Mars lacks sufficient volatile compounds to create an Earth-like atmosphere, even if you released everything available. A study published in 2018 by Bruce Jakosky and Christopher Edwards found that there isn't enough CO2 remaining on Mars to terraform the planet using existing technologies. You'd need to import massive quantities of volatiles from somewhere else, perhaps comets, or the outer solar system moons, which would require technological capabilities far beyond what we currently possess. Even if technically feasible, terraforming raises profound ethical questions. Does humanity have the right to fundamentally transform another planet? Mars might harbor microbial life in subsurface environments. Would terraforming constitute genocide of any Martian organisms? Some argue that lifeless rocks have no rights, and humanity should feel free to modify Mars for our benefit. Others contend that planets have intrinsic value and shouldn't be altered, or that we should preserve Mars for scientific study in its natural state. My personal view is that partial terraforming, creating localized habitable zones while preserving most of Mars in its natural state, might be an acceptable middle ground. Perhaps someday, centuries from now, parts of Mars could have breathable air under transparent domes or in valleys sealed with force fields, if that technology ever exists, while other regions remain pristine for science and wilderness preservation. But this is speculative thinking about a future so distant it's almost meaningless to discuss. In the nearer term, the next 50 to 100 years, Mars will remain a harsh frontier requiring constant technological support for human survival. Success will be measured not in transformed landscapes but in sustainable habitats, growing populations, and increasing independence from Earth. The Mars of our grandchildren's era will likely still require spacesuits outside and artificial environments inside, but it might host thousands of people living productive lives, conducting groundbreaking research, and building a new branch of human civilization. This brings me to the bigger picture. Mars is just the beginning. If humanity can successfully colonize Mars, we demonstrate the capability to live on worlds radically different from Earth. That opens up possibilities throughout the solar system and eventually beyond. The moons of Jupiter and Saturn, Europa, Titan, Enceladus offer unique environments that might harbor life and could potentially support human habitats. The asteroid belt contains resources that could support space-based industry and habitats. Looking further ahead, interstellar travel to other star systems represents an even greater challenge than Mars colonization. The nearest stars are light years away, requiring either generation ships that travel for centuries, suspended animation technology, or propulsion systems far beyond our current capabilities. But if we never take the first step to Mars, we'll never develop the knowledge and capabilities needed for these more ambitious goals. There's something profound about becoming a multi-planetary species. For 3.5 billion years, life on Earth has been confined to this single planet, vulnerable to extinction from asteroid impacts, supervolcanoes, or our own self-destructive tendencies. For the first time in Earth's history, one species, us, has the technological capability to establish life beyond our home planet. We have the opportunity to ensure that the story of Earth life doesn't end with Earth. That's not to say we should neglect Earth or treat it as disposable. Earth is our home, the only planet we know with vibrant ecosystems and billions of years of evolutionary heritage. Protecting Earth's environment and biodiversity must remain a top priority. But protecting Earth and expanding to Mars aren't mutually exclusive goals, they're complementary. The same long-term thinking, technological innovation, and global cooperation needed for Mars colonization also helps us address Earth's environmental challenges. In closing, going to Mars and potentially never coming back isn't a bug, it's a feature. It represents humanity's transition from a single-planet species to a multi-planetary civilization. It's a challenging, dangerous, expensive, and uncertain endeavor that will test the limits of human capability and endurance. People will sacrifice their lives, missions will fail, progress will be slower and harder than optimists predict. But it's also humanity at its best, reaching for goals beyond immediate survival, driven by curiosity and the desire to expand our horizons, working together to solve problems that no individual or single nation could solve alone, and building a future that extends beyond our own lifetimes. The first humans who walk on Mars, who live there permanently, who perhaps die there without ever returning to Earth, those people will be pioneers in the truest sense, opening a new chapter in the human story. Mars is calling. The question isn't whether we'll answer, but when, how, and who among us will take that irreversible step into humanity's future. For those brave enough to go knowing they might never return, they'll trade the familiar comforts of Earth for the opportunity to be among the first to call another world home. That's not a sacrifice, it's the adventure of a lifetime, the chance to be part of something far greater than any individual life. And when we look back centuries from now at this moment in history, when humanity first became a multi-planetary species, those pioneers who went to Mars will be remembered not for what they left behind, but for what they helped create, a new branch of human civilization, adapted to a new world, carrying forward the spirit of exploration that defines our species at its best. If you made this far, make sure to subscribe and give this video a like. And if the challenges of Mars colonization fascinate you, you'll want to explore an even bigger question. Why might expanding across the galaxy be fundamentally impossible? The obstacles that make Mars difficult might be nothing compared to the barriers facing any civilization trying to spread among the stars. The video is at the left side of the screen. It's a must-watch.